In this video, we will discuss about eutectic point and eutectic reaction. For this, we will look at another phase diagram of lead tin alloy. Lead tin, lead tin alloy. So, in the x-axis you have lead and tin. So x-axis is arranged in the percentage of tin. So towards right it is 100, here it is 0, and somewhere here it is 60, and here it is 80, and here it is 40, and here it is 20. And the melting point of lead is 327 degrees Celsius, and the melting point of tin is 232 degrees Celsius. So, suppose we have made an alloy of 60% tin and 40% lead. So what will be its melting point? Let us try to predict it using the phase diagram. We have already seen the phase diagram of copper and nickel, and we know what is liquidus and what is solidus. But let us make a linear approximation, and we think that it's so. Just we predicted that its melting point be 327 plus 232 by 2. Okay, but the real case, this was not so. So the actual melting point of this alloy, that is 60% tin and 40% lead, is at 183 degrees Celsius. Okay, it is at 183 degrees Celsius. So let me draw that line. So that temperature is very important. And the phase diagram actually looks like this. And so these are the solidus and solidus. So let me draw that clearly. So, this one is the, so here let me mark the various lines here. So this one is the liquidus line. Okay, this is also liquidus line. We have seen what a liquidus line is. Above that line, you have complete liquid. And here you have a solidus line. And so this line is also a solidus line. And this is a solvus line. It is called a solvus line. We have to see what exactly is a solvus line. And in this region between liquidus and solidus, you have L plus alpha, and here you have L plus beta. Okay, here you have alpha, and here you have beta, and in this region you have alpha plus beta. Okay, so let us understand the phases. These alpha and beta, these both are solid phases. Okay, both are solid phases of lead and tin, and liquid is a different phase. Okay, so liquid is the liquid phase. So let us draw the uh, see what is a liquidus line is. Yes, this is liquidus line. So liquidus line is the interface between liquid and liquid plus alpha, or liquid bar liquid plus beta. Okay, you can see these two lines. Okay, this liquid and liquid plus alpha, here liquid and liquid plus beta. Right. And this solidus line is the interface between liquid plus alpha and alpha, and then liquid plus beta and beta. Okay. So, so this is the solidus line. And so this is the solidus line, and this solvus line is so. What solvus line? Solvus line is the interface between alpha and alpha plus beta. Okay, so that is the interface between the different phases of the solid. So alpha and alpha beta, or you can say that it's the interface between beta and alpha plus beta. So these two lines are the solvus lines. And so let us call this point A. So this is the important point, and this point is called, that A point is called the eutectic point. Okay, eutectic point. Eutectic actually means it is called easy melting. That means and this composition, okay, so that is the composition. Actually, the composition is the right composition is 62 percentage tin and 38 percentage lead. Okay. At this composition, this alloy melts at 183 degrees Celsius, and this temperature is called the eutectic temperature. Okay. And this is how the eutectic temperature. You can see that if you look for any other combination, it does not melt at 180 degrees. The lowest melting point is achieved at this 62 percentage. Okay. Okay. Let me mark some more here. So see here the percentage is 18 here, and here it is 97. Okay. So 18 percentage tin and 97 percentage tin. So what happens at this eutectic reaction? What happens at this eutectic reaction? So at the eutectic reaction here, that is liquid alloy gets converted to alpha and beta. And the composition of the liquid is 62 percentage tin and 38 percentage. That is the composition at the eutectic point. At this point, the liquid is converted to a solid structure, that is a lamellar structure of alpha and beta. So this is called a eutectic mixture. This is called a eutectic mixture, or you can call it a eutectic microconstituent. Microconstituent, right? And what will be the composition of this alloy? So to say the composition is 18 percentage tin, and here it is 97 percentage tin. The remaining will be lead. So this is the composition of alpha and beta. To get that, see how I got that, because this was discussed in the previous lecture, how to draw the tie line and how to find the composition of the faces. So that means we are drawing a tie line here just below the eutectic reaction, and you can find that when the electric reaction takes place, the composition corresponds to this point, so that is 18 percentage, and here the composition of beta corresponds to this point, that is the 97 percentage. So this is how I found this 18 percentage tin and 97 percentage tin. So this is a eutectic reaction. Okay, and this reaction is an example of, this is an example of invariant reaction. Example of invariant reaction. And why it is called an invariant reaction? Invariant reaction means you cannot vary any parameters. For example, you cannot change the composition of the liquid here, and the composition of alpha cannot be changed, and composition of the beta cannot be changed, and temperature cannot be changed. Okay, will not be. All this will be a constant. For example, here composition of liquid is 62 percentage tin, and here it is 18 percentage tin, and composition of beta is 97 percentage tin, and temperature is 183 degrees Celsius. If you change any of this temperature, you will not get a eutectic reaction. If you change any of this temperature, composition, etc., you will not get a eutectic reaction. That is why this is called an invariant reaction. Now let us look at the microstructure you are getting. Okay. The microstructure evolution in a eutectic reaction. What is the change in the microstructure? So you can see that there is a liquid here. So you have the liquid, and this is converted to, see, upon on eutectic reaction. So this occurs. So you can see that. Okay, so this is how this alpha and beta is formed. Okay, let me draw this. Okay, this is how this composition will looks like. Okay. So these are the lamellar structure you will find. So here it will be, and this is the alpha, and this white region is the, see, the white region is the beta, the beta phase. So you will get a kind of lamellar structure during the eutectic reaction.